For each module, we've prepared a short PowerPoint presentation with audio like this one. The purpose of these slides is to orient you to the module, to introduce some key concepts, and to provide material for you to refer back to. One of the key commands in R is the assignment of something to a variable. In this example, we assign the number 5 to the variable a. We do this using a combination of keystrokes, the less than sign followed by the hyphen, which creates this arrow so that 5 points to a. Now, in this session of R, whenever we refer to a, we're referring to the number 5, as you can see from this print command. Additionally, R has the same arithmetic operations that you'd find on a standard calculator, so we can add and subtract, multiply and divide. And in a similar way to scientific calculators, R can also do advanced arithmetic. Here we're showing some examples where we're raising numbers to a power, taking the exponent of numbers, and the logarithm to various bases. Beyond this sort of arithmetic, R can also work in a logical sense. In these examples, we first see that we're using the double equal sign. We're asking, does the value on the left-hand side equal the value on the right-hand side? So when we have 4 double equals 6, R returns the answer false, but when we have 6 double equals 6, the answer is true. Note that true and false can also be treated like 1 or 0, 1 for true, 0 for false, so that the answer to the expression does 6 equal 6 multiplied by 3 is actually 3, because the first part of this expression in parentheses evaluates to true, which is the same as 1. We can also ask if numbers differ from each other. We use this with the negation equals sign. So an exclamation point and an equal sign is asking, is 4 different from 6? The answer to that is true. And lastly, we can think about inequalities, shown by the final example. Is 4 bigger than 6? The answer to which is false. Here we summarize the common logical operators that are used in R, most of which we've seen on the previous examples. As we start to put together more and more commands, it becomes useful to put these in an R program, which we call a script. These are written in an editor, and most modern editors have handy tools like syntax highlighting so that key words might appear in a different color or bolded. And they also often have error checking to guide us to where we may have made a mistake in the code. Importantly, you can also add comment lines. In R, this is done using the hash symbol. So we see in the example below, we're assigning the number 3 to the variable a, and we're making a note to ourselves exactly what we've done so that when we come back, we'll understand our own code much better. Some general good practices for scripting are laid out in this prototypical script on the slide that begins with a header where we might put comments about the functions, the author, contact information, and dates, for example. We may then first load in the packages that we're going to need, and then declare functions that we're going to use. Finally, we would load in any data that's going to be used before we perform our analysis. We would go about things in this way because scripts in R are evaluated in sequence from top to bottom. In this workshop, we're going to use and create functions. These are small programs within programs to automate common tasks. There are many advantages to using functions, including the interpretability, so that rather than writing out a lot of code that does something mysterious, we can give it a name that's very memorable so that every time we use it, we're clear about what we're doing. It can help to simplify our code because we need to define the function only once and can use it in many places. And it's a robust method because it reduces the frequency of mistakes. Provided we get our function right in the first place, we'll know that we're going to use it correctly in later parts of the code. There are three main components to any function. First, we have to give it a name. Second, we have to specify the arguments of the function. In other words, what information is the function acting on? And finally, we need to have a body of code that performs the analysis that we want to do within this function. This becomes a little clearer with the use of an example. Here, we're creating a function and we've given it the name mean. The argument of the function is x. Inside the function, we have the body of the code, where we say that s is the sum of x, n is the length of x, and m is the ratio of the sum to the number of values. We then return the final calculation m, and so that the function in its demonstrated use works in the way we would expect, where we provide the numbers 2, 6, 8, and 4, and when we ask for the mean, we get what we were expecting. This slide illustrates the importance of checking values. We're trying to create a weighted mean so that our function has two arguments, the values x and their weights w. The body of the code calculates a weighted mean and returns it, and in the demonstrated use, we see that we have supplied 4 observations and their corresponding weights, and the calculation works just fine. However, what would happen if we had 4 observations but only 3 weights? We see that R is able to perform a calculation, but we don't really know what it's done. Has it recycled the first weight to the 4th observation, or maybe used the last weight again? If we don't know how the function's working, we can't be sure to trust the results. What we can do instead is write a more robust function that first checks the length of x and the length of w are the same. If they're not, it throws an error and stops. Otherwise, it calculates. This will help the user make sure they're using the function in the way that's intended. We recommend Google's R style guide when writing scripts and functions. For functions, you'll note that we use comment lines to verbally explain what the function's doing, to be clear to define what the arguments are, and also what the function is returning. This style also includes error handling labels and also a label to explicitly locate where the computation is being done. Throughout several parts of the workshop, you'll be introduced to pipes, which are part of the Magritte R package in R. And it's a tool that helps us clearly express a sequence of multiple operations. You'll see this again in the data wrangling, data modeling, and data visualization sections, and so you will get further information on pipes. In this example, we'll show you a short piece of R code and then the equivalent version using pipes. So in the first standard example, we take 100 random variables drawn from the normal distribution and assign them to x. Then we create something called y, which is a matrix. It takes x and splits it into 2 columns. Last, we plot y, in other words, those 2 columns against each other, labeling them variable 1 and variable 2, and we see the plot at the bottom of this slide. Using pipes from the Magritte R package, we see that the code becomes more readable. We first generate our 100 random variables, then we pass them through the pipe into a matrix function and split them into 2 columns, and then we pass that result to the plotting function, generating exactly the same plot as we obtained earlier. A key part of scientific programming is the flow of control. We illustrate this here with a few examples that you'll meet throughout the modules. Conditional execution means only perform a calculation if a certain condition is met. And so it introduces us to keywords like if, else, and if else. We can also create loops so that we can perform calculations over and over again. We can do a for loop, which goes through a certain number of iterations. We can have a while loop that carries on going through the loop while a certain condition is satisfied. And we can repeat loops as well. For flow in loops, we can use the commands break and next in order to get out of loops or move on to the next iteration. We illustrate flow of control with 3 simple examples here, and you can always ask us for help with more complicated examples. In this first example, we assign the number 1 to A and the number 2 to B. We then say, if A is equal to 1, then assign B to C, and then print C. As R sees it, it first asks the question, does A equal 1? Because that's true, it sets C to be equal to B, so that when we print C, it is also 2, as is B. In this related example, we use if and else. First we ask, if A equals 2, then set C to be equal to B. Else, if that's not true, set C to be equal to A plus B. Well, because A doesn't equal 2, we actually go down to that later part of the expression where C is set to A plus B, so that when we print C, it takes the value 3. In the final conditional execution example, we make use of the if-else function. This has 3 arguments. The first is the condition, the second is what to do if the condition is satisfied, and the third is what to do if the condition is not satisfied. So in one go, we have if-else. Does A equal 2? If so, assign C to be equal to B. Otherwise, assign C to be equal to A plus B. In this looping example, we're creating a vector J that stores different numbers in different positions. We begin by putting 0 in the first position, and then we iterate so that we can create 5 more positions. Each one takes the value of the position and multiplies it by 2, so that we get the sequence of numbers 0, 2, 4, 6, 8, 10. Loops don't simply have to help us do numerical work. We can also add letters to words, for example, as we see where we go through this prefix of B, C, M, and R, and each time add it to the word at to create the words bat, cat, mat, and rat. This quick introduction to scientific programming isn't going to answer all of the questions in the modules. When you need more help, don't forget to ask us, and for particular functions, you can type the function name in the console window, prefaced by a question mark, and hit return. And what you'll see in the Help tab is the description, the usage, arguments, details, value, and references, and perhaps most importantly, worked examples for any given function, which should help you overcome certain difficulties. And again, we're always here to help. We'd now like you to navigate to the programming module on ELC and download the programming RMD file and upload it to the RStudio server. And you can begin working through the step-by-step instructions. Please note that you may also need to go to the data files section of ELC to obtain and download certain data. If you have any trouble, let us know.